Okay, I hear the recording in progress and share the screen. Okay, so we're up to 11.3. So we're here. I'm just about to show you the quiz. And we were supposed to finish 11.3 Monday. I think I'll finish 11.3 very early today. Won't take me that long at all. So it looks like I'm a day ahead on the game plan here. Okay. And 11.4 is on the comparison test. And you may have gotten a couple of Canvas announcements from me that there's actually some workshops from the CSM Math Resource Center if you would like to show up to those. It's optional, of course, on the comparison test. And I think they're holding them next week, so it kind of fits perfectly with what we have. Something else about the homework. The homework wasn't really that long, 3 to 25 odd. And part of it I'm going to make even shorter. I believe I showed you the homework. If not, I'll go ahead and show it to you again. It's no big deal. So 11.3, if I get that focused there. Page 725. So we're all doing the integral test. The basic idea is integrate. Whatever happens to the integral happens to the series. If the integral converges, so does the series. If the integral diverges, so does the series. Okay. And there we go. Problem 17. It's probably better not to do the integral test. We're going to use LCT, something called the limit comparison test. I'll talk about that in the next section. So you can integrate it if you want to. It's kind of cumbersome. Okay. So I would say put that on hold, solve it with limit comparison test. That's the next chapter. Likewise for 25, you don't really want to integrate that. Also use limit comparison test. That's LCT. That's an L there. Can't really see it. Okay, so in other words, hold off on 17 and 25 until you learn about something called the limit comparison test. Okay, you don't even have to write this down if you don't want to. I'll repeat it in the next section. Okay, the next section is the comparison tests, plural. Okay. So there's more than one comparison test. One of them is called the comparison test. And the other one is called the limit comparison test. Page 729. But I'm getting ahead of myself. I'm saving that for Monday. Okay, so I'll show you the quiz. Do only a handful of problems from here, and then we'll be done. Okay, so quiz time. Get ready to get your cell phone to take a picture or do a screenshot. Okay, let me make this a little bit smaller. And this last time, some of it got cut off. Okay. Number one, you were given a recursive sequence. A1 is 3, so they're already telling you the first term. And a sub n plus 1 equals 4n minus 3. Write down the first 5 terms of the sequence. Okay, so no big deal. The basic pattern is starting with the first number, plug into here, that gives you the second number, then plug it back in to get the third number, then plug it in, right? Just keep following that pattern. It should not be that hard. Okay, I think the number at the end ends up pretty big, but that shouldn't really bother you that much. Number 2, determine if the sequence converges or diverges. If it converges, find the limit. A sub n equals limit n plus 2, ln n plus 2 minus ln of n. Okay, a hint is use properties of logs. Okay, how do you take care of ln of a difference? All right, that should pretty much help you with that. Number 3, determine if the series is convergent or divergent. So this one's a series. These two are sequences. This is a series. And if the series converges, find its sum. Notice the index begins at 0. So you plug in 0. And then you plug in 1 and 2. To get a feel of what's going on, plug in 0, plug in 1, plug in 2, plug in 3. You should be able to recognize it after that. Okay. And well, I mean, look at the stuff that we've done. We haven't done that much stuff as of now. In fact, we've done very little. Well, you can just say there's no integral test here. So all the stuff has to be from 11.1 and 11.2 for the quiz. Okay. So there's the quiz. I'm going to make it disappear in a couple of seconds. So take your screenshot or take a picture, or it's on the video. You can get the video later. Open everything, but do the problems as in class, and it's due at 11:59 p.m. tonight. Okay. So any quick questions on the quiz? Otherwise, I'll make it disappear. And I'll give you time. I'll end early so you can get started early on it also. All right, so I'll make it disappear. I will assume that you're good, or you can always watch the video later. Many of you are getting this, from the video because I know you're not in class right now. All right, so we are back to the integral test. 11.3. You hit the highlights. Page 721. Put this on your cheat sheet. If f is continuous, positive, and decreasing, okay, so the function that we're considering has to satisfy that, and they generally will. Okay, so continuous, positive, and decreasing. Essentially, whatever happens to the integral happens to the series. So if the integral converges, series converges. You can just put I, C, S, C. If the integral diverges, I, D, then the series diverges. S, D is good enough for me. Okay, but you will have to prove it. Okay, prove it by the integral test. And a result of the integral test is the rule for P series. So put this on your cheat sheet, page 722. If you have summation of 1 over n to the p power, this converges if p is bigger than 1, divergent if p is less than or equal to 1. If p is equal to 1, you have summation of 1 over n, that's our harmonic series. Our harmonic series diverges. Okay, you can prove that with the integral test. Or in the previous section, they showed that you could essentially keep adding halves. It ended up looking like 1/2 plus 1/2 plus 1/2 plus 1/2. And so if you keep doing that, you get an infinite sum. All right, so I did some problems last time. I'll do a few more, and then we're going to end probably pretty quick, unless anybody has any questions. All right, number 11. 1 plus 1/8 plus 1 over 27 plus 1 over 64. Okay, this is like 1 over 1 cubed. This is 2 cubed, 3 cubed, 4 cubed. So this is summation of 1 over n cubed. That converges. That's a P series where P is 3, and that's bigger than 1. Okay, so I'm directly using the rule for P series. Okay, and notice also, all we're saying is the series converges, period. Okay. Quite often we'll be stuck with this. Maybe it sounds like an unsatisfactory conclusion. All you know is that the series converges. A natural question is, converges to what? What's the real number that it converges to? We don't know. We may never know. In fact, even today, this very day, there is some series where all you know is that the series converges, and nobody knows exactly what it converges to. I mean, you can do approximations. You can mimic this. You can have a computer go up to 1 million terms or 1 billion terms or whatever, but that doesn't prove, what the infinite sum eventually will be. Okay, so a lot of times in this chapter, all we can conclude is that the series converges. Converges to what? We don't know. We just know it converges, period. Okay, 15. Okay, summation of radical n plus 4 over n squared. Okay, here's a case where you want to split it into 2. So break it up into S1 and S2. This is capital S for the sum, just like before when we were doing integrals, right? I had capital I and then I1 and I2 for integrals within the same question, same problem. So S is my standard for the original series, and I have an S1, S2. So break it up into radical n over n squared plus 4 over n squared. So S is S1 plus S2. Okay, this one I can rewrite as summation of 1 over n to the 3 halves. Notice the lazy notation. If we already know we're doing an infinite series, we're not really concerned about starting at 1 or 0 or 2, whatever. Just quickly write summation, that's fine. All right, this is n to the half divided by n squared. That comes out to be 1 over n to the 3 halves. That's a convergent P series. It's a P series where P is 3 halves. That's bigger than 1, right? Move for P series on page 722. P series, summation 1 over n to the P is convergent. P is bigger than 1, divergent, and P is less than or equal to 1. 3 halves is bigger than 1, so this series converges. S2, summation of 4 over n squared. I can factor out the 4. That's one of the properties of series. 4 times summation of 1 over n squared. And this converges. I mentioned quickly last time that it converges to pi squared over 6. Okay, and if you multiply it by constant, then the whole thing converges to what? 4 pi squared over 6. So you get a convergent series. So this converges, same reason, it's a P series where P is 2, which is greater than 1. So this converges to a real number. This converges to a real number. Real number plus real number is a real number. So S also converges. Okay. Okay, then 21. And I was going to be done, folks, after that. I might sneak in just a little bit of the comparison test, but otherwise we'll be done very quickly. Summation n equals 2 to infinity. Can you see why they don't start at 1? Put a 1 here, you're taking ln of 1. ln of 1 is 0. You'd be divided by 0. So starting at 2. That's okay, that's allowed. So use the integral test, which means just change this to an integral. Change n to x. So integral from 2 to infinity of 1 over x ln x dx. It's continuous. Rational functions, continuous. Ln, continuous. Product or quotient, continuous. It's positive, and it's decreasing. Right. So limit b approach infinity, integral from 2 to b, 1 over x ln x dx. I do see a function in its derivative. The derivative of ln x is 1 over x. So it looks like a good u substitution. U equals ln x. Du is 1 over x dx. It's 1 over x there. Change the limits. X is 2. U is ln 2. X is b. U equals natural log of b. So my new integral is the limit is b equals infinity. I'm now going from natural log of 2 to natural log of b. I have 1 over ln x, that's 1 over u. And then 1 over x dx is my du. So limit b approaching infinity, ln absolute value of u, going from ln2 to ln b. So limit b approaching infinity, ln b an absolute value, but that's positive because b gets big, that'll be big, minus ln2. ln2 is positive, so you can drop the bars. And that approaches infinity. See, when b gets big, ln big is big, and ln of that big is also big. If I subtract that puny number, it's still going to be big, so infinity. All right, conclusion. Since the integral diverges, so the series diverges by the integral test. INT, you can abbreviate for integral test. Okay, I'm done, folks. So I'm going to mark off 11.3 as being finished. Originally, I wasn't going to finish 11.3 until Monday. I'm done today. It's not even 8:30 yet. Okay, I'm going to blab just a little bit as an introduction to what's heading up next week on the comparison test, and then I'll let you go unless anybody has some questions and you can get started on the quiz. Okay. So next up is something called the comparison tests. So page 727, comparison tests. Okay. The actual comparison test is at the bottom there. I'll just mention that it's there. I'm not even going to talk about it much now. I'll just show you my version of it. Okay. This comparison test is actually easier to understand, but it's less useful. More useful is 729, the limit comparison test. And there it is. I'll talk about it next week. And abbreviations. We don't want to keep writing the whole thing. So CT, comparison test, I will write CT. Limit comparison test, LCT, as you might guess. All right, so if you want to see the comparison test in the text, it's on the bottom of 727. I'll just show it to you quickly for those of you who don't have the book and aren't getting it. Okay, it's correct. There's nothing wrong with it. But I'll give you my variation. All right, so comparison test. Given two series, summation A sub n, summation B sub n, notice the lazy notation, not writing, n equals 1 to infinity or 0 to infinity, whatever, and you only have positive terms. Suppose A sub n is less than or equal to B sub n for all n. And so the picture would be something like this. Now, we already believe the integral test is true. So even though, strictly speaking, what's going on is we have finite points, labeled by the x's, you can kind of smooth out the function. Okay. So I'm employing the integral test. Whatever happens to the integral happens to the series, right? So the B sub n's, the B sub n's are larger than the A sub n's. All right, suppose summation of the A sub n's diverge. This series diverges, translated to an integral. You have an infinite amount of area under this curve. What does it mean about the B sub n's? You have an infinite amount of area under the curve. Translation, summation of B sub n also diverges. That's one version of the comparison test. The other variation, summation of the B sub n's converge. The bigger series converges. You have a finite area under that curve. What does it tell me about summation of A sub n? Also converges, right? How can you have an infinite amount of area here when the bigger graph, the bigger series already is finite? Okay. That's the way the comparison test works. Okay. If summation A sub n diverges, the smaller series diverges. Anything bigger diverges. If the bigger series converges, the smaller series has to converge. And the thing that's a little bit tricky, but I think you can probably see why. If either of these is true, you cannot make any conclusion. B sub n diverges. The bigger series diverges. You can't say anything about this. It might converge, it might diverge. And the other situation where you can make no conclusion, summation A sub n converges. The smaller series converges, then I don't know about this one. It might converge, it might diverge, right? Sort of a comparison. It's a comparison. You're comparing with something bigger or smaller than you. Okay. I guess I can just give a money analogy. Okay, I'm talking about a millionaire. I'm guessing most of us aren't millionaires, otherwise we probably wouldn't be doing what we're doing now, including myself. Okay, so you're a millionaire. Okay, a million is real rich. Okay, suppose I say so-and-so has more money than a millionaire. You have more money than someone who's rich. Well, they got to be rich, right? But if I say, oh, so-and-so has less money than a millionaire, less money than a millionaire, well, I don't know, right? They still could be rich or they could not be, right? That would be this comparison kind of thing here. You know, I can make no conclusion about that, right? And in the other extreme, you know, you and I sometimes make comparisons like this. You know, so-and-so is a very poor person. They have hardly any money. And then you say, oh, somebody has less money than that poor person. Okay, less money than the poor person. That means they're also poor, right? But how about the other way? So-and-so has more money than that poor person. More money than, well, right? They still might be poor or they might be rich. They might be millionaires, right? You can make no conclusion. So that's sort of the way you want to think of this comparison test. Okay. The smaller series diverges this bit. That's like saying richer than a millionaire. Okay, then they're a millionaire. The bigger series converges, anything smaller converges. Okay. You have less money than a poor person. Okay, and then they're also poor. Here are the cases where you can make no conclusion. Okay. The big money, the big series diverges, can't make any conclusion at this. That would be like saying, I have less money than a millionaire. Well, that's, you know, you still might be rich or you might be penniless. You can make no conclusion. And this one, the smaller series converges. Okay, then what can I say about anything bigger? I don't know. Okay. So I have more money than that poor person over there. More money than the poor person. Well, you still might be poor. You might be medium. You might be, you know, upper class, middle class, or a millionaire. You can't say. That's the basic idea behind the comparison test. So I just want to give you that introduction because it saves me from having to do that on Monday. So Monday, we'll probably get started with the comparison test in earnest. But otherwise, that was going to be it for today. And I'll let you get going on the quiz, but let me check to see if anybody has any questions. Check the chat, and I don't see anything offhand. All right, any questions? Otherwise, I'll let you go and get started on the quiz. All right, so have a good weekend. Get going on the quiz. Do it at 11:59 p.m. Open everything, but do it like we did in class. All right, bye everybody. Have a good weekend.
Thank you.